Hello and welcome to this lesson. We're going to be finishing off the bits on enantiomers that we didn't finish last week, and then we'll start some of the reactions. So what we're going to start off with is just some examples of optical isomers. And is that Andrew? Hi Andrew. I've just started the lesson because apologies for the change in time, and glad you could make it. So, Andrew, in terms of optical isomers, think about what's needed. I'm just going to go over it, but remember it's the asymmetric carbon. Do you know what an asymmetric carbon means? What will it need? Hi, Andrew. 4 different groups. So as you can see in that example there, I've got a green fluorine group, I've got a methyl group, I've got a OH group, and I've got a hydrogen peeping in the back. So this middle carbon over here, central carbon, is an asymmetric carbon, also called a chiral carbon. So that's what I've said over there. And when you answer this, for excellence, show that you understand what you mean, so you identify the chiral carbon. You say C2 or C3 or something like that. And then, of course, the molecule is also chiral. Now, there I've just tried to show that if a compound is chiral, the two mirror images don't superimpose on top of each other. So I can turn it and spin it, but I'll never get all 4 groups matching up. So there I turned it, so I could get the green ones one matching up, but the methyl and the hydrogen didn't. So let's have a look to make sure you've understood what a chiral carbon is, or chiral molecule. Number 1, is that chiral? Will that show, can you make enantiomers out of that? So you can either say a yes or a no. No, correct. And the reason why not is because it's got 2 methyl groups, so I don't have 4 different groups. I've got a hydrogen, an ethyl, and 2 methyls. What about number 2? Is that chiral or not? So that was no for the first one, and yes it is. And think of identifying which one is it. Now you'll have to start numbering from the left because the ketone is higher than a hydroxy group. So it's 1, 2, 3, 4. It's carbon number 3. Correct. What about number 3, molecule 3? Is that chiral? And if so, which carbon? Okay, it actually is chiral because this carbon, C2, has got a methyl group, a hydrogen, a chlorine, and an ethyl. So it's got 4 different groups on that one. And then the last ones, for number 4, is there anyone over here? Yes, there is. And would you like to have a go which one? This will, of course, this one will be C1 because it's got the lowest one. So C3, correct. It'll be that one because it's got an ethyl, a chlorine, a hydrogen, and a chloroethyl. And a chloroethyl is different to an ethyl. Okay, so you've got it clear in your head how to recognize a compound that can be chiral. Now what we're going to do is over here, I've drawn them in 3D because we've got to see, are these enantiomers? In other words, are they mirror images of each other? And I've misspelled enantiomers. It's E-N-A-N. Sorry about that. So are they mirror images? So you can't superimpose them. So if you look at number 1, is the second molecule over here reflecting the first molecule? So is it a mirror image? Yes, it is. So those are 2 enantiomers, or a pair of enantiomers. Now that one was easy because it's showing the mirror image very clearly. If I take any molecule though and I swap a pair of groups, then I will get the mirror image. So the 2, 3, and 4, I've shown it differently. I'm still showing it in 3D, but I can swap pairs around here more easily. So is the first one, is this number 2, a pair of enantiomers? So you're typing there while you type. Okay, you are correct. It is not. And the reason is, so first of all, that was a yes for the mirror images for the first one. The reason it is not is because it actually is not a chiral carbon or a chiral molecule. I have got two hydrogens on this central carbon. There they are. And of course, we can't have a chiral, or we can't have an enantiomer if we don't have a chiral carbon. So I don't know in the exams, I haven't seen that before where they trick you, but they could ask you something like that. Right. Oh, I've given the answer for that one. Now, this one is an example where they are not mirror images of each other. And the reason is because two pairs have been swapped around. So if you look at the one on the left, I've got an ethyl at the top. So I'm just trying to see where there it is. I've got an ethyl at the top and a hydrogen at the bottom. And can you see they've been swapped here? I don't have to swap opposite pairs, I just have to swap any pair. But there I've done a one swap. Now here I've got a methyl on the left and a amine on the right. Whereas here I've got an amine on the left and a methyl on the right. So can you see that these two have been swapped around? And because they've been swapped around, this molecule 2 on this, or molecule on the right, is exactly the same on the molecule on the left. And the best way to do this, and you can do it in the exams as well, take 4 differently colored pens, or different looking pens, so this sort of thing. If you have 4 different ones, you can reverse them around and you can see which group is which and if they superimpose or not. So I might show that later on in a later lesson, because I haven't got 4 different colored pens with me now. For the very last one, number 4, is that one showing a pair of enantiomers? You're not sure? So have a look, see if there are 4 different groups first of all, and if a pair has been swapped or 2 pairs. Right, you're not sure? Okay, it is, because what we've got here is a bromine on the left and an ethyl on the right, and the same thing here. So we haven't changed the bromine and the ethyl, but we have swapped one pair, a hydrogen and a methyl. Now the methyl's on the top and the hydrogen's at the bottom. So that those 2 molecules are a pair of enantiomers, because I've only swapped a single pair. Do you think you'd be able to work out if something's a pair of enantiomers or not, and if something's chiral? So you are typing there. Yeah, sorry. You got to swap two. If you swap 2 pairs of groups, then they will not be enantiomers. So number 3 is an example of that, where I swapped the ethyl hydrogen pair and I swapped the amine methyl pair. So if you swap 2 pairs in your diagram, then you've actually drawn the original one again. I've tried to show it in the booklets where you swap a pair and then you swap a second pair and you land up with the first one again, first molecule again. Okay, right. What I want to do now is the physical properties. So a lot of this is based on what you did in the 3040 series on polarity of molecules and the physical properties. So we're going to flip through all 11 functional groups, because one of the questions they ask, they don't ask you in the detail of why a molecule is polar or not, but they do expect you to be able to work out their physical properties and to differentiate based on their physical and chemical properties. So if I take an alkane, I've only got hydrogens and carbons singly bonded, and I've got a very, very small dipole moment. It's so small, we say this is non-polar. Okay, you always think of alkanes, oils, they're non-polar. Right, and because they're non-polar, they only have temporary dipole attractions. And will it be soluble in water? No, correct. So that's sparingly soluble or insoluble. And For something like an alkane, it's a gas or perhaps a liquid, depending on how long the chain is. I doubt that they'd give you really long chained ones like 18 carbons plus, that would be a solid. So an alkane is pretty much a gas or a liquid. They start becoming liquids round about hexane. Pentane is the borderline, and then hexane, heptane, and octane from petrol. So that would be a liquid, but otherwise gas or liquid. The example I gave you, butane, that is a gas. Right, an alkene. Can you see the dipole moment is also very small there? It's 0.35. It's a little bit higher than the alkanes because of the double bond. So we can consider it to be nonpolar, so we say it's still temporary dipole attractions. The permanent dipole attractions are really weak because it's such a really weak dipole moment there, so we can pretty much ignore them, and it's not soluble. And so again, this particular molecule is a gas, but otherwise for alkenes, the ones that you're going to come across in organic chemistry at this level are either going to be gaseous or they're going to be perhaps a liquid. Okay, hello alkanes. Can you see the dipole is getting much bigger now because of that electronegative chlorine, which is also so it's changing the polarity of the molecule. It's not just hydrogens and carbons anymore. So you're going to have the permanent and the temporary dipole attractions. So it's still not going to be very soluble in spite of having those permanent dipoles, because it can't hydrogen bond with water. Water won't bond very easily with this, so it's not going to dissolve very easily. It'll just dissolve slightly. Okay. But because of its high mass, is it going to be a gas, a liquid, or a solid? So it's 64. It's a liquid, correct. So this one is, this particular, I said gas liquid because I'm talking about haloalkanes in total. This particular one here, with the boiling point at room temperature, it's already a gas. So chloroethane is a gas, but if I went to chloropropane, it's already starting to become a liquid. So this particular one's a gas, but haloalkanes are the liquids, and only a few of them are gases. So let's go very quickly here. Alcohols, this now has hydrogen bonding with it. So as long as the carbon chain is not too long, it's going to be soluble in water. Miscible just simply means it dissolves completely in water. It mixes in all proportions. So if I have 1 part water and 5 parts ethanol, or this alcohol, it'll dissolve. Or if I had 1 part alcohol and 5 parts water, it'll still dissolve. And you can see from the boiling point, it's a liquid at room temperature. So most alcohols that you'll come across will be a liquid at room temperature. Amines, you can see it's also got a dipole moment, and it can do hydrogen bonding because of that NH2. So it's going to be soluble. And this is a key thing. It's soluble and makes a basic solution. It's really important for you to remember, because that's one of the things of how you can distinguish it, because you can use litmus to test it. If the litmus turns blue, the only organic functional group you know of that is basic is an amine. So very important one. And again, it's a liquid. So alkanes, alkenes tend to be gases, but it may be liquids if they're big enough. The rest you're going to come across are going to be pretty much all liquids apart from one. So let's go through it quite quickly. Aldehydes, you can see that dipole increasing. Although it can't form hydrogen bonds itself, water can form hydrogen bonds with it. The H of the water molecule can be attracted to the lone pair on the oxygen, so it will dissolve. Again, though, the longer the chain, the less likely it will dissolve, and it's a liquid. Ketones, the same sort of thing, slightly bigger dipole, and you know that acetone dissolves in water, but again, the longer the chain, the less likely it will dissolve, but this is a liquid. Amide. Now, an amide has an enormous dipole compared to the others. The others were all 1 or 2 something. This is 3 something, nearly 4. It's an enormous one. The reason is, and you would have done it at university, but it's not needed at level 3, but it's the reason is the nitrogen doesn't hold on to its electrons as tightly as oxygen, so it can donate it, because oxygen on the other end is pulling the the electrons away. So if nitrogen donates its electrons, oxygen can grab, yes, it's polarizing, oxygen can grab the electrons in the double bond to itself because it's got a higher electronegativity. So I've got a much stronger dipole moment for the molecule. And because it's so much stronger, an amide can have strong permanent dipole forces of attraction as well as hydrogen bonding, and of course the temporary. So what you're going to find, it's going to dissolve, and very importantly, this is the only solid you get. We'll be showing a reaction in the next lesson where as you make the amide, you'll just see this white precipitate coming out. So you're working with liquids and suddenly the solid appears, and you know you've got an amide. Okay, look at its boiling point, 221 degrees. Right, carboxylic acid, this is the vinegar that you know of, the ethanoic acid, and of course you know it's hydrogen bonding, so it's going to be soluble, and this will form an acidic solution. It's not going to be the only one that forms an acidic solution, it'll be one of them. So if you test with litmus and it goes red, then it is likely to be a carboxylic acid, but we'll come across the other one just now. And of course it's a liquid. Then esters can't form hydrogen bonds, so they, although this particular one I've given you here because it's only got 2 carbons in it, very few alkyl parts, it will dissolve, but any other one, so ethyl ethanoate won't dissolve in water. Okay, so esters, consider them to be not soluble in water or only slightly soluble, but it is a liquid. Acyl chlorides, this is the other one. The acyl chloride is very reactive, and we'll see that 3 lessons down the track. And what happens, it reacts explosively with water. It's not that explosive with water, but it will form bubbles and so on as it releases the HCl gas, and some of that HCl will dissolve in the water and of course form an acidic solution. Right, and that's also liquid. So just summarizing, we had the alkenes, alkynes as being gases, perhaps the haloalkanes, but otherwise from haloalkanes onwards it's liquids, and we had 1 solid. And pretty much a number of them are soluble in water, but not the alkenes and the alkanes and the haloalkanes. So that's sort of as an overview. So if we were trying to identify a substance, so they could say, here you're given 4 unknown substances. They could be this, 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 and this. Draw up a plan to work out what they are. Then what you can first look at is, are they gases, liquids, or solids? So if it's a solid, it's an amide. Unless you get given a really big molecule, which is highly unlikely. By big, I mean carbon atoms greater than 18 or 20 for an alkane, or greater than at least 15 or so for something else. Yes, and of course the polymers. Okay. If it's a liquid, you must probably, in this sort of style, as I say, the alkanes and alkenes can also fit in here if they got, say, 5 or 6 carbon atoms in them. But that's the first thing. Is it a gas? Is it a liquid or solid? That gives you an idea. I did notice, I think it was last year or the year before, they gave you solutions of the substance, so you couldn't use gas, liquid, or solid to identify it. This flow chart is to give an idea of when they say draw up a method to separate, to work out what's what. First test is always put it into water. If you put it into water, okay, if it doesn't dissolve, then you've got 1 group. If it dissolves, you've got another group, and of course the explosion one is the acyl chloride. That's a reaction that we'll be looking at later. If it doesn't dissolve, it could either sink in the water, and then it's normally a haloalkane, or the others tend to float on the water. Again, it does depend on the mass of the organic substance, but it tends to float. Okay, so that's the alkanes, alkenes, esters, aldehydes or ketones. If they're long chained, they won't dissolve. If they're short chained, they will dissolve. Now, I've just put this in here because we haven't done reactions yet, but we do distinguish the alkenes by two chemical tests, which we'll hopefully look later today if there's enough time available. And that you've got to remember when you're doing these sort of flowchart type things. Otherwise, if a substance dissolves, you test with litmus. If it turns blue, it's easy. You've got an amine. So only one that'll go and form an amine. If it turns red, it's acidic. Now remember that the acyl chloride also forms an acidic solution. I should have perhaps put an arrow here as well, because it also turns red. And then if it doesn't affect litmus, you've got something that's neutral. So it could be an alcohol, it could be an amide, it could be an aldehyde or ketone. And we do have chemical tests to distinguish that, which we'll do later. So it's oxidation, or we use what we call the silver mirror test, or the Benedict's or the Fellings test. But I'll do those later. But that's a good slide to remember, because there's generally some sort of question that will use those properties that come up in the exam. Okay, what I'm just going to do here is just move this along so you can see the solubility. Okay. Sorry, I'll move it along. So what they've got here in the first one is ethanol. They're adding water to ethanol, and you can see it's totally soluble. There's ethanoic acid, totally soluble. This is the ester. And can you see the ester has formed the two layers, where the ester has floated on top, and that's totally soluble, and that's totally soluble. So it's the ethanol and the ketone, the propanone. So they're all soluble except for the ethyl acetate. Right, so just, as I say, you can always Google that YouTube clip if you want to see the whole thing. So that's it in terms of the 305-1, where we've looked at naming of compounds, drawing of compounds, isomers. So we had the constitutional isomers, the geometric isomers, and the enantiomers. And then you had to look at the physical properties. But the physical properties are, as I say, not the detail of the 3040 series, it's just simply how we use it. So you've got to be able to work out, are they polar or non-polar in general, and whether they will therefore dissolve in water or not, and so on. So now I'm just going to start 305-2, which is the reactions. And the first thing we'll do in that first chapter is the 7 tips. If you keep these in the back of your mind, then it will help you in all the rest of that book in terms of the types of reactions. So the first thing is your organic reactions are slow. And that's because you're breaking covalent bonds. When you're reacting ionic compounds, they're already separated in solution. So you don't have to break strong bonds. They're already separated. They're ready to react. With organic, you've got to break bonds. So it involves heat normally, and it involves time for that to happen. Okay, so we use what I've said there, the water baths or heating mantles and magnetic stirrer bars, and I'll show what I mean here. So this is the heating mantle. You can see it's heated. This has been set up as a distillation system. You can see we need special glassware. That's not normal that you've come across in your inorganic reactions. Can you see there's a magnetic stir plate here? That's because there's a little magnet on there which stirs it around, and that just makes sure when we heat the substance, it doesn't just all heat up, and it's like a pot that doesn't bubble nice. It might just make one enormous bubble and shoot up and go all over the place. Well, here it'll just go straight down. You don't necessarily have to wrap it like this one. Here they have wrapped it. There's a thermometer that you use because you've got to check what substance at what boiling point it comes over, and then you collect it over here. This is done under a dry system. It might be we're collecting something that isn't allowed to come into contact with water. But this is what we call a distillation setup. Right, so what I've got here, and actually these may take a bit of time to load because I didn't load them out beforehand. So I suggest have a look at these two videos. So I've got the JHUA Adams has done one, and David Reed has done the other. It shows you how to set it up. Last year this did come up in the exams. So there's the distillation setup. They haven't put a heating mantle here. They're going to use a Bunsen burner. You can only do that if you haven't got a flammable organic molecule. So here you can just see how they're adding it, filling it up, and how they're connecting it together. I just wanted to show a little bit more. There they're setting it up. And I just want you to see how they connect the water. So the water comes in one side and out the other side. So it's always in the lower side and out the upper side. And I'm going to leave it at that. Have you done a distillation before? Yes. Okay, so you know how to set it up. Right. So otherwise, have a look. It's really important you know how to do it. And there it's coming through. So here it's just an open beaker. Right. So I'm going to move on to the next one. This shows the reflux. So distillation, did you notice I was boiling it in one end and it was distilling over and cooling down and dropping out the other side. What we're going to do here is, this is when you want the reaction to needs heat to keep on going, but as I heat it, my reactants are going to evaporate. Now I don't want them to evaporate because I want them to break up. So I'll just move this on a bit more quickly. Sorry. So there they're adding the anti-bumping granules. So something's always added, either magnetic stirrer or anti-bumping granules. And here they're connecting it up. I'm going to move it a bit further. Now can you see what's happening? It's heating here, but as it evaporates, it's cooling by that cold water that's coming in from the bottom and going out the top, and it's going to just drip back in again. So this is what we call a reflux. And we do need to, so that we don't boil off our reactant. So can you see it's boiling away, and I want to get it down again because I want it to keep on reacting. Okay, so let's go on to the next one. And this needs something. This is when you've got your substance, you've reacted it. Say you're reacting an organic compound that doesn't dissolve with an aqueous substance like dichromate, then you're going to need to separate them. They'll separate the insoluble organic layer from the aqueous layer. And this is what we call a separating funnel, or separatory funnel, as they say in America. So I'm just going to move it up. And it's the point is to, so there they're adding it on. They're just simply washing it there to make sure they've got all the organic. Now they're shaking it. And I'm just going to pause it here. And one of what we call the workups is when you add, if you've got an acidic substance, so like dichromate, we normally acidify it, then we want to get rid of that acid. And what we do is we add sodium bicarbonate or sodium hydrogen carbonate, because you know carbonate reacts with acids. And when that does, it gives off a gas and it fizzes, and you'll notice you'll be opening the tap there. Can you see, just open it and close it, and he shakes it to make sure all the bicarb has reacted with the acid. And that's one way of what we say is a workup. And if I just move it a bit further, then he's moved it down, and now he's letting the organic layer move into the flask. So I don't know if you've done that technique as well. And this point here is drying, because there's always a little bit of wet in our substance, even though we've separated out. So we add the something that's like sodium sulfate, and when it's very floury, then you know it's absorbed all the water and there's no more water left. If it's clumpy, then it's still got to absorb, there's more water there. So again, I strongly recommend you watch this video so that you know about those techniques. Right. Okay, I can see you typing there. Okay, good. Now, the other, so tip number 3, so the first one was organic reactions are slow. This next one is the specialized glassware. So you need to know the reflux setup, you need to know the distillation setup, you need to know about that separating funnel and how, when we use it, and the drying. Okay. The third tip is knowing the type of reaction, and you need to know 5 types. First is addition. Addition only happens to alkenes or alkynes, but we don't do alkynes in level 3. So something is added to each carbon of the double bond. An elimination is when we have something like a halogen or an hydroxy group that can get taken off, plus a hydrogen from a adjacent carbon. So if this chlorine comes off, it's got to be either one of these blue carbons. It can be any one of those blue carbons, but one of them also has to come off, and then we form an alkene. So elimination is when we have either an alcohol or a haloalkane where 2 atoms have to come off, 2 adjacent or 2 atoms on adjacent carbons to form an alkene. So addition, you go from an alkene to, say, an haloalkane or alkene to an alcohol. Elimination is when you do the reverse. Substitution is when I take, say, that chlorine and I remove the chlorine and I replace it with something else. So in this case, I've taken the chlorine and I've replaced it with an OH. So that's what we call a substitution reaction. They can ask you to discuss the different types of reactions, so you do need to know what they are. Oxidation. Now, if you've done redox, that goes into depth. In terms of organic, all we really consider for oxidation and reduction is oxidation is either adding oxygen or removing hydrogens. So, for instance, this was an oxidation reaction to go from the OH to the ketone because I've removed a hydrogen. Okay, you can work out the oxidation numbers. It's just a bit more complicated because the oxidation number of this carbon is actually different to the oxidation numbers of the other carbons. So we don't bother going into oxidation numbers. We just see it more as either adding oxygen or removing hydrogen. If we reduce it, the other one is reduction. Is, for instance, if I'm going from here back to the alcohol, then can you see I've added a hydrogen? So that's one way to recognize it. Have we added oxygens, or have we removed hydrogens, or have we added hydrogens or removed oxygens? And the last one is acid-base, and that will affect the carboxylic acid because being an acid will react with a base. And the base would be an amine. Okay, so keep those in the back of your mind as you work through. As I finish each chapter, I try to identify the reactions as one of those 5, so keep track of that. Then, I find a lot of students don't know where the change happens. So this is what this tip is identify the reactive site. So you look for the functional group because that is where the change is going to happen. And what sort of change is going to happen? It's if you look at the electronegativity of the groups attached to that carbon, you can work out, get a good idea of what's going to happen. So knowing your trends that you did in the last set of booklets is a good idea. So you know nitrogen, oxygen and fluorine are very electronegative. Yeah, I can see you typing there, but as you're typing I'll just carry on. Okay, is the stoichiometry only related to the functional group? Okay, by stoichiometry we use that word when we talk about balancing equations, like we need 2 of one to react with 1 of the other, or we need 2 of this to react with 3 of that. So, and that's just with a balanced equation. In organic, because we aren't that fussed over things like if the equation is balanced or not. Although if you have to, when you work out the recipe, in other words the method, you must make sure we you add enough of the reactants. So in that way it's related to the functional group. Did I answer your question? Yeah. Okay. Right. So as I say, we have to work out if the carbon atom is electron rich or electron poor. So if it's been attracted to something more electronegative, then the electronegative atom is going to drag its electron density away. So there I've got three different types: an alkane, an alcohol, and a carboxylic acid. Now there's very little difference in electronegativity. 2.5, 2.1, carbon's slightly more electron rich, but we basically always consider alkanes and alkenes as nonpolar. Okay, with an alcohol, the OH is 3.5 in terms of electronegativity, carbon's 2.5. There's a much bigger difference in electronegativity. And on this side, we've got this poor carbon having its electrons dragged up by an oxygen over here, as well as by the oxygen down below. So if you have a look, this carbon is slightly positive because it's got electrons being withdrawn. This carbon is a lot more positive because it's got electrons being withdrawn by two oxygens. So alkanes have little reactivity. They really don't do much. You'll learn two reactions and that's it. Alcohols are a lot more reactive, and they're what we call attacked by nucleophiles. Philes means loving, okay, so nuclear loving positive. So a nucleophile will be electron rich in itself, so OH minus is a nucleophile because it's a negative ion, so it's electron rich. NH3, ammonia, is a nucleophile because ammonia's got a lone pair, it doesn't mind sharing. So anything that's electron rich or has got a lone pair, it doesn't mind being shared, will react with something that's electron poor, as in this carbon over here. And the same thing, carboxylic acid, the carbon is attacked by a nucleophile. Now, a good thing to know is which bond is going to break. So over here in the alkanes, we're going to ignore that because there's little reactivity. If I'm going to attack this with a nucleophile, you want to break a bond that is going to come away easily. Now, carbon, remember, can only have 4 bonds. So if I'm getting an electron-rich substance coming and attacking here, it's bringing in electrons, which means any one of these groups have to go with a pair of electrons. So if this OH comes off as OH minus, so think of it, if it comes off, it's OH minus. If this methyl comes off, so I'm just trying to see my cursor, there it is. If a methyl comes off, it comes off as an alkyde, methide, CH3 minus. Have you heard of CH3 minus? Is it a common thing, as common as OH minus? No, it isn't. You're quite right. So that carbon-carbon bond is not going to break very easily, because if it does break, it's a very strong non-polar bond. An alkyde is going to form, which is immediately going to bond back on again because it's so reactive. So the more polar the bond, the more easily it breaks, pretty much. The CH bond we know is not particularly polar either, and if it had to come off, the hydrogen would come off as hydride. And again, hydride, it is around, but it's not as common as OH minus. It's a much stronger base than OH minus. So the most polar bond is going to break. Now, in this one, which bond is going to break? The double bond, the carbon-carbon bond, or the CO bond over here? The CO bond, because again, I've got just simply hydroxide coming off, whereas to break a double bond needs a heck of a lot of energy. Okay, so let's look at the next step now, because we spoke a bit about it before, about what's the leaving group. Is it an alkyde, an hydroxide, or a hydride? The more neutral that leaving group, the more easily it'll leave, and won't attack back again, and therefore the more reactive the molecule. So as an example here, I've got an amide, a carboxylic acid, and a acyl chloride. Now, if something attacks, a nucleophile attacks that carbon in each case, I'm going to, okay, there I'm just showing the polarity. So where it's going to break, it's the polar bond's going to break. So I'm having this NH2 minus leaving. Okay, so NH2 minus, it's, have you come across that before? No, it's a very, very strong base. Okay, you've come across NH3, but can you imagine removing a hydrogen? Can you imagine NH3 acting as a proton, like an acid, a proton donor? It leaves you as NH2 minus. It's got to be a really, really strong base. Whereas if I've got a carboxylic acid, I've got OH as a leaving group. Now OH, you know, is a strong base, but it's a much weaker base than NH2 minus. Compared with the acyl chloride, okay, I'm going to have a chlorine, or a chloride leaving. Now chloride, you know, is neutral, pH of 7. So of those, chloride is the best leaving group. So which of these three is going to be the most reactive? The acyl chloride, the carboxylic acid, or the amide? The acyl chloride. That's why when you add it to water, it will get rid of its chlorine very quickly because it's such a good leaving group. Whereas a carboxylic acid will just dissolve and an amide will just dissolve. It won't do anything. If anything, the carboxylic acid being an acid, it will break a bond here. It'll give off an H+, whereas that won't do anything. It'll just simply dissolve. Right, so it's good to think of what the leaving group is because that'll help you with the reactivity. And I have mentioned before why the CH3C bond doesn't break, because you're going to have an alkyde being formed, CH3 minus, and that is just too ridiculously strongly basic that it will just simply add on again. You'll need way too much energy to break that non-polar CC bond. Okay, 6th tip, so we're nearly there. Reaction conditions. As you go through it, because you need to be able to explain what the reaction conditions are, what reagents you need. So learn those reaction conditions because some of them are very similar. So as an example, if I've got a primary alcohol, if I use acidified dichromate, I can form either an aldehyde or a carboxylic acid. What makes it go to aldehyde, what makes it go to a carboxylic acid is my reaction conditions. So if I distill it, so as my alcohol is changing to an aldehyde, because the aldehyde is a lower melting point than the alcohol, I can distill it off to form the aldehyde. If I don't distill it off, if I keep it in my solution and by reflux, so it all drips down again, then my aldehyde is going to react further. So it's basically alcohol, aldehyde, straight to carboxylic acid. So take very careful note of the reaction conditions. Don't just sort of say, oh, it's dichromate, because you're not going to be marked correct. You have to be very specific. It's acidified dichromate under distillation conditions, or it's acidified dichromate under reflux. And as we go through, I'm going to point out some similarities all along, so you're just aware of those very similar reaction conditions, but big enough to be a difference. Then the final step is also what you learned last year, is the major and minor products. Organic chemistry, unfortunately, it's not as though you can react A to form B and you get 100% of B. What will happen if I react A, I'll get mainly B, but I'll get a bit of C, and I might get a bit of D, and I might get a bit of E and F as well. So it tends to be a bit mucky. And there are two rules, though, that are helpful, which will make you remember what are the major and the minor products. Markovnikov is to do with addition. So if you think of A is the beginning of the alphabet, addition, Markovnikov, M comes before Z, so it's higher up in the alphabet. So Markovnikov's related to addition, and the shorthand way of remembering it is the rich get richer. Okay, so chemistry and society unfortunately often coincide too much. So what we mean by the rich get richer is the carbon that's got the most number of hydrogen atoms attached to it, that's what we mean by rich, is going to get the incoming hydrogen. So don't in an exam say Markovnikov's rule states the rich gets richer. You won't get anything for that. You'll have to say the carbon with the most number of hydrogens atoms will get the hydrogen atom, the incoming hydrogen atom. So here I've got water and concentrated sulfuric acid. This is my rich carbon because it's got 2, whereas my other one has only got 1. So can you see my yellow carbon is more rich in hydrogens than my red one? So the incoming hydrogen is going to go to the yellow. So can you see there were my 2 and I've added the hydrogen to that. And my OH, because I'm adding on HOH. So HOH, that's what I've added on. If you like, the conc H2SO4 is like a catalyst to get it going. And so my OH is going to come on the other carbon that's got the least number of hydrogen atoms. It's really important to work out. And that's my minor product. So that's where it's done the opposite, where the OH has actually gone to the rich carbon. You will get some of that, but most of it is going to go the other way. Now, Zaitsev's rule, so if you think of elimination, E for elimination comes after A for addition, and Z for Zaitsev comes after M for Markovnikov in terms of the alphabet. So it's one way of not mixing them up, is the poor get poorer. Okay, so the carbon that's got the least number of hydrogens is going to have to give up any hydrogens it's already got. So here we've got a molecule. So there is my OH. So the red carbon is where it's all going to happen. Now I've got to take from an adjacent carbon atom. So the adjacent one is, if I can just see my cursor, is the blue one. So I can either take from this blue one or I can take from the yellow one. Now which one has got the least number of hydrogens, the blue or the yellow? The blue. So the major product here is going to be where the double bond forms between the red and the blue. Sorry, I'm just highlighting those two. So that's my major product because I've taken from the blue. The poor get poorer. And my minor product is where the reverse happens, where it didn't work. Now, what I've also, why I've chosen this particular example as well is, did you notice the reaction conditions? Both of them involve concentrated sulfuric acid, but they give different products. And that's because this is in water. It sounds a bit ridiculous. Why not to say dilute H2SO4? But you actually have to add the conc H2SO4 and then the water. So it's done in 2 steps for that. Whereas here, I just simply add conc H2SO4 and heat. Elimination tends to be always the more extreme conditions. So here, if you like, it's been like diluted and I'm not adding too much heat. Here, though, I've got to heat more strongly. So if I'm eliminating, if I'm taking away, it normally has to be more harsh conditions. So make sure you don't just say conc H2SO4. Notice which one is only conc H2SO4 and heat and which one actually has the water added. Okay, so those were the end of the tips. So what we want to do now in the last 10 minutes is do a bit of the reactions, and we may finish off with a game that you can play. So let's go for it. This is very briefly what you learned last year, reactions of alkanes, and they've only got 2 reactions. They either burn, so this is an example of methane that gets trapped in ice, so it's from the internet, and otherwise it does react with chlorine under UV light. So it's a level 2 reaction, and you are expected to know level 2 for level 3, so I'm just mentioning it there. Now with the alkenes, they are a lot more reactive. Having that double bond there gives us a lot more options. So there are 4 reactions you need to know and 2 tests. And those are hydrogenation. Okay, so I've taken my alkene, my double bond, and I've added hydrogen to each one. So hydrogen, you can see the hydrogenation, hydrogenation. My next one is halogenation. So I could have reacted with Br2 or Cl2 or I2, but the Br2 is the one that you need to know as a test. So that's why I've highlighted it here. The next one is hydration. If you hydrate, you're having water, so you're adding water, HOH. So it's H2, halogen, this is HOH. And then the final one is hydrohalogenation. So adding HBr or HCl or HI. So I'm adding an H and a halogen. So you can try saying that fast 10 times. Hydrogenation, halogenation, hydration, hydrohalogenation. See if you get tongue-tied or not. So those are the 4 reactions. And then the 2 tests. So remember when we spoke about identifying what a substance is, and we had that flow chart, dissolving it in water and so on, and then it was testing it. To test if something is alkene, you can either use bromine, so I'll get both of these going at the same time. So what we've got is alkane and alkene, and we're going to be adding bromine to it. Now if it's added to the alkane, don't worry about the one below. This first 2 is the same thing with adding the bromine to it. Can you see to an alkane, it will react with time, but it's a very, very slow reaction. So that bromine, that brown liquid we're adding, doesn't disappear because it's a very slow reaction. But hopefully it'll do to the alkene now. There you go. As we're doing it to the alkene, can you see it disappears instantaneously? So that's what we mean by decolorizing bromine water. That color just disappears. So that's one test. This test, I'm going to move it on because it was doing the same thing over there. If I move it on to the permanganate, now they didn't use acidified permanganate, so you're not going to get a colorless solution here. I'm going to move it further on. Okay, they've added something there now, and it hasn't changed the color. You can see it's still purple, and I'm going to move it on and move it on a bit more. Can you see they've now added the alkene to it and shaken it up, and can you see it's gone brown? There's been a reaction. So we've actually formed a diol over here. Okay, so let's now check what is added to each carbon of the double bond. So with halogenation, it's Br2, so I've added a Br to each one, and there's my product. Hydrogenation, I've added an H to each one, and there's my product. The permanganate test, it's acidified permanganate, so you don't have to acidify it, but if you're talking about decolorizing the purple, then you have to have it acidified. And I haven't drawn, unfortunately, because I didn't have enough space, but it forms a diol, so I add an OH and an OH. Then hydration, I add an H and an OH, so there you go, and remember Markovnikov's rule. And hydrohalogenation, remember Markovnikov's rule. You didn't have to worry about Markovnikov here or there, because there we didn't have a hydrogen to add, and here both were hydrogens, so it didn't matter. And so there's my product. So let's match these up. Hydration, I should have actually numbered them so you could just put the names in, but have a look and I'll do the answers now. Okay, right. So I'm trying to work out what the con meant. Okay, so the concentrated sulfuric acid and the H2O, correct? Yep. Okay, halogenation is a Br2. Hydrohalogenation, okay, I'm slightly ahead of you there. There I've used HCl and not HBr, but it's still, I could also use HBr, correct, both of those. And hydrogenation is the top one. And then where the brown color fades is which one? Okay, it's Br2, because Br2 is brown, so you do that. And the test where the purple color fades is the permanganate. Sorry, I've gone a bit faster than you. Okay, so I just want to finish off with this in the last 5 minutes. I have got something on OTL. It's really looking at level 2, but it's with the alkenes that you can do. I haven't really done much for level 3 with all the extra reactions, but it's enough for the alkenes to get you going, and I'll slowly add some more. So keep those in mind, those 4 reactions, and then you can play this game. So it's basically you deal 7 cards. If you've played Rummy, then you know how to play it. So each player gets 4 cards, and you need to get rid of them in sets of 3 or more. So that would the aim of the game is to get rid of your cards. Okay, and you can add on to sets that have already been formed, and then you have to discard a card at the end. And then, of course, the first player who gets rid of their cards wins. So here I've got, the deck normally should be showing the other way around, that you don't actually know what you're picking up, but just for this online thing, I'm just trying to show you what it is. So that's normally showing HBR, but that would be the other side of the card. So they've got their 7 cards, player A, player B. So player A has to pick up a card. Now you've got to look, what can you make out of that set? So he's got an alkene. Okay, he's got an OH. Can you form something from an alkene to the OH? So I want to go quite quickly because there's only a few minutes left, but he can use that to form the OH. Now he could have also put the card major product down. I have done it this time round because that is the major product if you use a Makovnikov's. And now he's got to throw a card away. So that's player A's turn. Player B, so sorry, I just tidied that up a bit. Player B now has to pick up a card, and he has to look, and he's got no alkene there, so he can't really do much. Okay, as you learn more reactions for the other types, it becomes a lot more flexible, but we're only dealing with alkenes here. So he just throws away a card. Back to player A, he picks up a card, he can't do anything there, so he just discards off one of his reactant cards. Now it's player B's turn, he picks something up, he still can't do anything because he hasn't got an alkene. He could carry on from there, but he's not doing that at the moment. So player A picks something up, can't do anything, throws it away. Player B, aha, he's picked up an alkene. Can he do something? No, he can't, because actually he didn't have any of the reagents. He didn't have HCl to form that. He didn't have H2 to form that. And he didn't have the conc H2SO4 and H2O to form this. So he couldn't do that. So back to player A, he picks up a card, can't do anything, throws it away. Player B's turn now, picks up a card. He's got now an alkene. He's got the H2 that can form the alkane. So he puts those down. Okay, minor product and major product don't come in this one, so that doesn't help. You can't get rid of that, so he gets rid of a reagent card. Player A's turn, picks up a card. He's got an alkene and he's got the reagents to form that, so he's won. He's got rid of his cards first. Because player A started, I thought, well, let me go one more time, and it just turned out that if player B now gets a card, he actually can get rid of his cards too, and this is, he can say, okay, I'm starting with an alkene, and I'm going to flip that around because I want to go in this direction, and I'm going to make my alcohol. Now it's a primary alcohol, so I can put my minor card down. Then I can say my alkene over here can also form that alkane, and so I can now get rid of my last card. So it's up to you whether player A has won or whether player A and player B have won, because I'll leave it like. But that is a game you could play with somebody, and it'll make you think of major and minor products. It'll make you think of your reagents and your reactants and your products, and you've also got to look at you see it from all angles, and as I say, as we go into more of the reactions, you'll get a better idea when we do reaction schemes. Okay, it's past. Any questions? Okay, I have a question for you. Do you think you would play that game? Do you think it would be useful to learn reagents? You might actually know all these already, but do you think it'll be a useful way of? Okay, because I've got you'll have to make I mean, I've done it on a PDF. You'll just have to cut up the cards, and if you just print it on paper, you might have to put it back onto cardboard. But it's just a way of trying to make it a bit more fun, because there is a lot of learning off by heart in this standard. It's a lot of off by heart learning. Oh, yes. I know when I go to the conference this in July, I want to, because I know there's some people there that can do a computer, where I can get it, so you can get it on an app and download it. But my HTML skills are not good enough. But it is certainly in the pipeline that I want it done. At the moment, it's only paper copies only. Right, it'll get there eventually. Okay, so we'll stop there, and next week it's Wednesday and Thursday, because I want a catch-up lesson. Right. Okay, so we should finish the organic chemistry next week, and then we'll go on to the spectroscopy, because I want to try and finish the spectroscopy this term, so we got 2 externals and 2 internals.